This lesson is over Unit 7.1, Intro to Equilibrium. So here we have reactions, two different reactions, and it's just showing that reactions are reversible. So we would say that this first reaction is the forward reaction, whereas the second one would be the reverse. Okay, so what we see with both of these reactions is that here we have our reactants, our A plus B yields our products C and D, and then we see that in the reverse reaction our products are actually acting as the reactants, and they are producing the products that were before considered reactants. Okay, so in these types of reactions, generally initially we start with only A and B, okay? So if we're doing an actual reaction, okay, and we're combining two reactants together, okay, we start with those original ingredients. There's no products being made. So only the forward reaction can occur. Okay, but as some of these reactants are becoming products, okay, the products are actually going to build up. So over time, as the reaction is continuing, C and D build up. Okay, and then the reverse reaction speeds up. Okay, and what happens to the forward reaction is that the forward reaction slows down. Okay, so like I said, we start here with the forward reaction. So as these reactants are used up and become products, okay, now that we have products, we can now have the reverse reaction occur. So this reaction is actually going to speed up, okay, whereas because we're using the reactants here to create these products, okay, this reaction is actually going to slow down, okay? And usually we don't go all the way to completion for either of these, which is kind of an important thing to note. We're going to get to this equilibrium. Okay, so that's what step 3 occurs. Eventually, the rates are equal. Okay, so the rate at which this reactant is becoming this product and the rate at which this product is becoming this reactant, okay, they're going to be equal. So basically the concentrations of any reactant or any product are going to remain the same, okay? And so this has to do with rates. The amount or the quantity, the concentrations of each of the species is not equal necessarily. It just is the rates are going to equal out. Okay, and we'll kind of see this in a graphical representation on the next slide. Okay, so here we have a graph where we have different species. We have A, B, and C. Okay, and here it's just proceeding through time. So we have a reaction that's occurring over time. Okay, and then on our y-axis, we have concentration. Okay, so it's showing us how much of each species we have over a certain amount of time. Okay, so notice that A and B both drop in concentration over time, whereas C is increasing in concentration over time. Okay, and we hit this point, and I would say it's probably about here-ish. Okay, and we'll just call this T1. At a certain time of T1, okay, we notice that the concentrations stop changing, okay? So at T1, the concentrations of all three species stops changing. okay, which is what I kind of explained on the previous slide, okay? But notice that all three of them have different concentrations, so they're not equal. They're just constant. Okay, so the concentration, for example, of A is no longer changing after that T1 time. The concentration of B is no longer changing after that certain time. Okay, so an important thing to note too is that once we've reached equilibrium, it does not mean that the reaction has stopped. Okay, and what it means by this, okay, so over time, we still have our reactants becoming products and our products becoming reactants, but the rate at which this is happening does not change the overall concentration of either, okay? So things are still occurring. We still have molecules breaking down or coming together in this case, and creating C, okay, and then the reverse reaction, C is decomposing into A and B, okay, it's just all happening at the same rate, so the concentrations don't change, okay, and we have a special term for this, which is dynamic equilibrium. Okay, so dynamic just means movement, so it's just telling us that even though we're at equilibrium, okay, there's still reactions that are occurring, we just don't have a change in concentrations. Okay, so in a chemical equation, the coefficients tell how much a species concentration will change prior to equilibrium. Okay, so if we look at this specific graph over here, okay, notice that species A started out at a concentration of 4, and then it dropped to about like 2.5, so it dropped about 1.5 moles per decimeter. Okay, and then B also dropped at that same rate. Okay, so that's why they never crossed. So they would both have the same coefficient out in front because they're both dropping at the same rate. Okay, or being used up in the same rate. Okay, for C, we notice that it also rises 1.5 concentration at equilibrium. So it would also have the same coefficient. So if we were writing out an equation for this, we would have A plus B yields C. Okay, if, for example, we had an equation, let's say we had A plus 2B yields C, okay, in this instance, it's telling us that we have to have 2 moles of B for every 1 mole of A. So we'll actually see a bigger drop, a more drastic drop in B before it levels out. Okay, so that's kind of how you can tell which species has different coefficients based on is it being consumed or produced at a faster rate. That's going to mean it has a coefficient. Okay, so when we're looking at rate, we generally look at the equilibrium constant, which is K. Okay, and we have different types of K. We're going to talk about 2 of them today. But if I have an equation, so let's say we have this equation. Okay, where the lowercase letters represent the coefficients, and then the uppercase letters represent the species of both my reactants and products. Okay, if we have KC, and the C just stands for concentration. Okay. How we would set it up for this particular equation we would have capital C raised to the lowercase c, and then capital D to the lowercase d, over capital A and brackets to the lowercase a, and then capital B to the lowercase b. Okay, and then that would be our equilibrium constant equation. Okay, so notice that on the top we include our products, okay, where we would put the concentration, for example, of C, okay, in the brackets, and then we'd raise it to whatever the coefficient is. Okay, same thing with D, and then in the bottom we have our reactants. Okay.